Hello everyone, welcome to my talk titled Intrinsic Lateral Inhibition Facilitates Winner-Take-All in Domain Wall Racetrack Arrays for Neuromorphic Computing. This work is a collaboration between UT Austin, UT Dallas, and the Sandia National Labs. Neuromorphic computing is a novel computing paradigm that is inspired by the structures and functionalities of the human brain. The computing units of the brain are neurons that communicate with each other through spikes, also called firing events. The motivation of this work comes from the fact that for the human brain to properly function, neural activities should be regulated. That is to say, in a neural ensemble, only a subgroup of neurons should fire to create meaningful representation of sensory information. Otherwise, if the neuronal activities fall into abnormal synchronization, the unregulated or explosive state of the human ensemble will lead to epilepsy or rather pathological consequences. Selective firing of the neural ensemble requires some form of neuronal competition to produce winner neurons that are allowed to fire. One proposed competition rule is the winner-take-all rule, which states that only the most strongly stimulated neurons are selected as winners and are able to fire. Depending on the number of winners and output format, WTA can be categorized into hard WTA with only one winner, KWTA with K winners, and soft WTA when the output of the WTA layer is proportional to the neuronal activities. WTA can be implemented with a mechanism called lateral inhibition, by which the more active neurons further inhibit the activity of their less active neighbors and prevent their firing. WTA models are often employed to study behavioral phenomena such as action selection, attention, and decision-making, but they also have powerful computational capability and are crucial building blocks of neural networks and machine learning algorithms. The WTA unit has been used to control sparsity in deep neural network, and it has also been shown that WTA can lead to efficient Hebbian learning. Mapping WTA unit to hardware, various CMOS circuits have been proposed, but they often require complex recurrent electrical connections. Therefore, to efficiently achieve lateral inhibition, it is desirable to utilize the intrinsic interaction between artificial neurons. Syntronic devices are gaining importance in neuromorphic computing due to their compact structure, high endurance, and non-volatility. The spintronic spiking neuron prototype studied in our group is a magnetic neuron called the three-terminal domain wall magnetic tunnel junction neuron, or the domain wall MTJ neuron. A cartoon showing the device structure and the SEM image of a device fabricated by our group is shown in the left two figures. The domain wall MTJ neuron consists of a racetrack for domain wall motion and an MTJ for spike readout, and can mimic the integrate and fire spiking neuron model. In this model, a neuron builds up its membrane potential by integrating input currents. Once the membrane potential reaches the firing thresholds, the neuron generates a spike, or action potential, to be sent to the post neuron, and is reset to the initial states. As shown in the figure on the right, during the integrate phase, current applied between the in and clock terminals of the domain wall racetrack drives the domain wall towards the MTJ by spin transfer torque or spin orbit torque. The magnetoresistance of the MTJ depends on the magnetization alignment of its two layers. Before the domain wall reaches the MTJ, the magnetization of the two layers of the MTJ are antiparallel, resulting in a high magnetoresistance and low output current. When the domain wall reaches the MTJ, the magnetoresistance of the MTJ is switched low and gives a high output current in the readout terminal. This mimics the fire of the neuron, and this action potential could be passed on to the input of the post neuron. Beside the integrate and fire function, The domain wall MTJ neuron also has intrinsic lateral inhibition. Intrinsic means that there are no electrical connections needed to facilitate the lateral inhibition between a pair of neurons, making our implementation simple and energy efficient. Although the magnetostatic interaction of spintronic devices is long considered undesirable, here we are taking advantage of it to facilitate competition between two neighboring domain wall MTJ neurons. We first define an active neuron to be the one with larger current input and higher domain wall velocity, because such neurons will fire early. In other words, neuronal activity is encoded in domain wall velocity. As sketched by the figure, in a pair of side-by-side domain wall MTJ neurons, the winner neuron imposes a magnetic field along the -z direction upon the domain wall of the loser neuron, further reducing its domain wall velocity and neuronal activity. We should also note that the loser neuron also exerts a stray field in a +z direction on the winner neuron. But as our previous study shows, such field has little effect on the domain wall motion. Based on the mechanism of lateral inhibition in our neuron prototype, we can quantify lateral inhibition as the velocity reduction delta V of the loser neuron due to lateral inhibition. It is important to notice that the magnitude of lateral inhibition of the domain wall MTJ neuron is related to material parameters, device geometry, and notably the spacing of the two neurons. This is addressed by our previous work where we explain this relation by micromagnetic simulations and an analytical model of current and field-driven domain wall motion. We are especially interested in the neuron spacing dependence of lateral inhibition, because the neuron spacing is a crucial parameter of a neuron array. Next, we expand our study of two-neuron inhibition to the inhibition behavior of a neuron array. We now consider a single layer of domain wall MTJ neurons, which are arranged into a 1D array. As is mentioned in the previous slide, the lateral inhibition parameter is a lateral distance dependent quantity. So lateral inhibition in an array is dependent on the neural array layout. We consider, for example, two layouts, the periodic and the diperiodic. In a neuron array, the magnetic field experienced by a domain wall is the contribution of all neuron devices. But as the device stray field rapidly decreases with distance, we can properly assume only nearest neighbor interaction. Therefore, the essential difference between these two layouts is whether the two nearest neighbors of each neurons are spatially symmetric. In the periodic layout, a neuron is only inhibited when both neighbors are more active, because otherwise, the stray field from both neighbors cancel each other. We refer to this inhibition scenario as case A, as highlighted in the figure. In contrast, in a diperiodic layout, a neuron has a larger probability of being inhibited because it always experiences a non-zero stray field. The two inhibition scenarios in the diperiodic array are referred to as case B and C. We shall see that the two layouts result in different lateral inhibition behavior of the array. In modeling lateral inhibition in a neuron array, we combine micromagnetic simulation and numerical calculations. Since it is not feasible to simulate in micromagnetic simulator a large array of magnetic devices, we extract a lateral inhibition model from two neuron inhibition simulation and numerically calculate the neural activities due to lateral inhibition. Given the neural array layout and the input current distribution, we first find the initial spatial distribution of domain wall velocity and neuron activity. And then, based on the lateral inhibition model, we decide which neurons should be inhibited and calculate the resulting domain wall velocity. The resulting domain wall velocity distribution should yield an enhanced neuronal activity contrast, and based on this result, we can calculate the neuron firing statistics. Domain wall velocity distribution under two assumptions of inhibition magnitudes are modeled. The first is weak inhibition, which means that the amount of inhibition will not result in any backward motions of the domain wall. The second is strong inhibition, which means that an inhibition is sufficiently strong so that the domain wall can have a negative velocity. In the case of negative domain wall velocity, no matter how large the time window for recording neuron firing events is, these neurons are prohibited from firing altogether. Here we show the results of an array of 1,000 neurons arranged in periodic or diperiodic layout, respectively. We first initialize a series of domain wall velocity of arbitrary unit between 1 and 3, and then randomly assign them to each neuron. For the periodic layout, the inhibition parameter is delta VA, and for the diperiodic layout, the parameter pair is delta VB and delta VC. The domain wall velocity distribution is calculated for a series of increasing inhibition strengths, and are then ranked from low to high such that we could visualize their distribution. It is observed that under both strong and weak inhibition, there is an enhanced velocity contrast, and diperiodic array layout has a larger overall domain wall velocity reduction due to the higher inhibition probability. On the other hand, the periodic layout has a higher nonlinearity of velocity distribution, which can be interpreted as a result of the more strict inhibition rule. The domain wall velocity distribution of the array can yield time domain and space domain neuron firing patterns. In recording the neuron firing events, the proportional of winning neurons depend on the size of the recording time window. It is convenient to define neuron firing proportion as the ratio of winning neurons under an infinitely large time window. Therefore, under strong inhibition, by which some neurons are prohibited from firing altogether, the quantity has a less than unity value. As expected, we can observe a decreasing neuron firing proportion with increasing inhibition strengths. Therefore, strong inhibition is analogous to the K winner-take-all, where K out of n neurons in the array are chosen as winners and fire. Comparing these two neural layouts, we see that diperiodic layout yields a smaller firing proportion, and is therefore more efficient in implementing KWTA. On the other hand, even under weak inhibition, we can still infer neuron activities by recording their firing timing. This mimics the soft winner-take-all, where the output of the WTA units are analog and proportional to the neuronal activities. In conclusion, in this study, we have shown that magnetostatic interaction between domain wall MTJ neurons can lead to intrinsic lateral inhibition and winner-take-all in a one-dimensional neuron array. Particularly, layout of the neuron array affects the domain wall velocity distribution, neuron firing statistics, and WTA efficiency. In our future work, we will explore more neuron array layouts that are biologically plausible and will enable beyond nearest neighbor interaction to achieve long-range or global lateral inhibition. We will also build a standard WTA building block to be integrated into realistic neuromorphic architectures. Finally, we are currently working on the experimental demonstration of the domain wall MTJ neuron lateral inhibition. This is the end of my talk. Thank you for listening,